So what is our next problem? The next problem is to straightway write down the Lagrangian density for the fields. And that is very important. That is as follows. The coordinates are AI. The generalized velocities are del I a k, or like this, del I a k. Okay, they are generalized velocities. And I said that your Lagrangian should be quadratic in generalized velocities. Okay. Now, do we know something about the generalized velocity or some quantity which can be constructed out of this del I a k? And that quantity is known to us already. It is like Fik, right? We know the definition of Fik. So this field strength tensor can be treated as the generalized velocity for the electromagnetic field. Okay, and of course these are the coordinates, and coordinates very well can be treated as the generalized coordinates. So henceforth we will talk about the field formulation and think of the potentials, four potentials, as the generalized coordinates, and the derivatives of the potentials, that is this one, as the generalized velocities, and they are nothing but the field strength tensor, the components of the field strength tensor, right? And as I said, the Lagrangian should be quadratic in generalized velocities, and generalized velocities are like this. So how do we construct a generalized quadratic term with this generalized velocity Fik? Also, we should not forget that L should also be Lagrange invariant. This is another important thing. So you have to satisfy all these conditions in order to construct the Lagrangian for the field, and it can be done like you can write this Fik, yes, Fik, and with this Fik, you can construct a Lagrange scalar quantity or Lagrange invariant quantity as Fik. We already know this, right? And some time back I gave you a problem also to find out what is the value of this quantity, and the answer is 2 times b square minus e square. Okay, so this is the value of this, and this is of course a Lagrange invariant quantity. It is also quadratic in the generalized velocity. Fik is the generalized velocity. So try to understand this, that now we are almost home in constructing this Lagrangian. I often call this Lagrangian density and as well as Lagrangian alone. But when I say Lagrangian, I mean the Lagrangian density. So please look at this terminology. In most of the textbooks, you don't always call it Lagrangian density. Sometimes you call it only Lagrangian. And when you say Lagrangian, you understand that you are talking about the Lagrangian density. So where do we go further with this? So now we have the Lagrangian density for the fields as minus 1 upon 16 pi, and then I write Fik and Fik, right? So here you have constructed a Lagrange scalar, and this 1 minus 1 upon 16 pi is a factor to make it compatible finally with the experiments, and also dimensionally correct. And then apart from it, you have another term, because the fields, as I told you yesterday also, the fields interact with the charged particles, which are sources. Now, the picture is something like this. You have the charged particles, right? Not just one. You can have Q1, Q2, Q3, or whatever. And they can be moving here and there in different directions. So basically what you have is Ji, right? So we call it Ji because Ji is a 4 vector which describes rho C. It also describes the currents. Okay. So these Ji or these charges create the fields. So if they create the fields, they are what? They are the sources. So you can call them the sources because they are creating the fields. So they are sources of the fields. Okay. So it is like Gangotri, out of which the river Gangas, that flows. And when you have to write down the Lagrangian for the fields, you cannot forget the sources or the parents from which these fields have been created. So you write another term to this, and that term is important. It is AI and JI. Okay. Now in tensors, this I is not the same I. Every term is independent. So this is a dummy index, AI, JI, and this has to be overall a Lagrangian scalar because this is Lagrangian scalar and this is a Lagrangian scalar quantity. Lagrangian is Lagrangian scalar. The first term is Lagrangian scalar. Therefore, the second term will also be Lagrangian scalar. And if you add anything to L, that should also be a Lagrangian scalar. So everything should be Lagrangian scalar. Okay. So we have constructed this quantity AIJI, where AI is the field potential and JI is the source. So the sources are also interacting with the fields, right? The sources are creating the fields are this, but they are also interacting with the fields. Okay, and later on I will show, and you can yourself see this, that this interaction is the same interaction which we were discussing yesterday. Okay. Yeah, you can always find out that this part which I have included here, which I have included here is the same thing which I was discussing yesterday while talking about the interaction, Lagrangian, interacting part of the Lagrangian of the charges with their fields. So let's just think of it like this again, that you have the sources of the inform the charges or currents. So this is the key quantity we are talking about, Ji. Ji is a 4 vector. And this Ji is interacting with the AI, that is the potentials of the fields. And that is source term is sitting here. Okay. So please see this like this. The source term is very, very important. Then if you are talking just of the fields without the sources, you can still talk about that, no problem. This is the part without the sources. So it is without the sources. So this term is also called free field, the contribution to free fields. So if I ask you what is the Lagrangian of the free fields, so you will tell me only this term. If I ask you what is the Lagrangian of the fields plus sources, okay, you will tell me this entire thing. And what are the Lagrangian just for the sources? So again, just for the sources, it is only this part. AIJI. So now you can see I have done the whole dissection before you of the Lagrangian of the fields plus sources. And if you have any questions, then you can ask me now. And henceforth, we will move to find out the field equations, which we call as the Maxwell's field equations. So how do we find those field equations is again a very straightforward matter. It does not require any great physics, but just some mathematical exercise. So what do? We write for the part, we have to write down the Lagrangian equation for this. So how do we write the Lagrangian equation? The Lagrangian equation has to be written for field. Okay, how do we write it? That is the question. So how did we write the Lagrangian equation for the particles? So for particles, if you remember, for particles, the Lagrangian equation was what? It was like d by dt and this del L by del V, right? Minus del L by del R is equal to 0, right? But now we have to write down for fields. So we have to make changes. And the very important changes that we cannot write d by dt because now we have to take the relativistic analog of this. So for fields, we have to write down not this, but del of del I. That means you have to include the derivatives with respect to what? With respect to time as well as with respect to space. So this is the first outer part, and then you write del, and then you write L. This is the Lagrangian density, because now for fields you will talk about the Lagrangian densities. And this V is the what? The derivatives of the generalized coordinates. So these are generalized velocities, and these generalized velocities I already told you would be written as del I A K. Okay. So this is this part. Okay. So this entire thing can be now written as this. Okay. Del by del t, d by dt. Look again. The first term outside this d by dt, this operator is changing now to del I. So it is now changing to del I. And then this Lagrangian is changing to Lagrangian density. The generalized velocity has now changed to this del I AK, because of the former slide. You can go back and see AK are the coordinates, and they have to take the 4 derivatives of this. So now minus and the second term. Now the second term is del L by del R. So I will write simply del L by del. In place of R, I will write the coordinates of the fields, which are nothing but AK. And there you are, you put it equal to 0. Okay. So please see, these are going to be our equations for our use. Okay, this has to be 0, and it is our equation now that we will be using. And in order to do this, we have to calculate the first part, this one, right, as well as the second. So this will be an exercise for you to do. I will give you some hints here and there, but you have to do it on your own. Okay, and try to find out, try to solve this equation, and then you go ahead with this. So in order to do this, first we will try to solve, or rather find this part. Which one? This, the first, that is del L by del I k. So let us try to find out this part. Now everyone can do it, so it is also a problem given to you, and you can solve it and return to me along with your other solutions to the problem. So we have to find del L by del I a k, right? This is the first thing. Once you find this, then you will put this, okay? So first you have to find this term. And you know L, so again write L, and in that you have the first term, free fields, the Lagrangian due to the free fields, which is minus 1 upon 16 pi. So just write it as minus 1 upon 16 pi, and fik. So you will write here what? Fik, and the second part of the Lagrangian will actually not contribute to this because it is the derivative with respect to del IAK. In the second part, you don't have this. You just have what? Del L by del, or rather, in the second part of the Lagrangian, you have what? You have, it is L first part plus L second part, right? Now, what was the L first part? L first part is this thing, and L second part was minus 1 by C AI JI or AMJM, if you want to use another symbol for this index, AMJM. Now, this AMJM or this part does not contain anything like the generalized velocities. Therefore, they are just the coordinates, field coordinates. As I told you, potentials are just the field coordinates. They are not the generalized velocities. Therefore, this term will not contribute while you calculate this. So you can omit all of this and get the contribution out of it. Now there is this factor of 1 over minus 1 over 16 pi, and you can forget it for the time being and just calculate what you can calculate what fik, but since here down below we have the same indices ik, so we have to change our terminology about the indices or the nomenclature. So better I should call it as FLM. Okay, because you know the dummy indices can be always changed, the nomenclature can be changed, there is nothing unusual. So I have intentionally changed it here because down below we have I and K, so it is not appropriate that I should keep the same indices on the upper side in the numerator as well. So I will change to LM. And so first you have to calculate this bracket, and then only you can do this, right? Now I give you the answer to this. You should calculate this, and before calculating it, it is actually quadratic in the generalized velocity, so you should be able to calculate just the first term and then the derivative of the second term, then the derivative of the second term, and just FLM like that. So as you do the normal derivative, you have to take the differentials. So you can also you can find out this whole value will actually or should come out to be like what? You can guess. This FLM is a scalar quantity. So can you see that? This is a scalar quantity. So it is rank 0. Down below you have I and K. So there are two indices down below. And therefore the whole expression has to be a tensor of rank 2. These I and K both are the contravariant indices, but they are sitting in the denominator. Therefore, they have to go like this. Okay. So in the final outcome, whatever you have, I don't know the real answer. Okay. It could be something like alpha, some number, let's say 4 or something. Okay. So alpha times Fik. But one thing I know that overall this expression should be like a tensor, and that tensor could be any tensor, right? It could be any tensor. So let me say this tensor is something like this, but it has to be a second rank tensor, and both the indices should be down, because here you have the contravariant indices in the denominator, and when you have something as the contravariant index and sitting in the denominator, then it behaves as the covariant index in the final, covariant indices in the final expression. Okay, so you have to calculate this, and when you do this, first you try to do a simple problem. That is, you just take one term, don't take both of them together. So just take one term, that is del f lm, and this del of del down below the same thing, I and k. Okay, it is simple to calculate. So first you calculate this thing, and then you go over to the quadratic term FLM. Okay, and just try to think about what should be done. Any question? Now, so having calculated this, you will return to the so-called Euler Lagrangian equation for the fields. Okay, Euler Lagrangian equation for the fields, right? And those equations I have already written, but I am just repeating them. You can use any kind of indices, any nomenclature of the indices, not the same as I am using. But if you use the same, it will be del I, and then of course this. Okay, minus del L by del AK. Please see the straight lines are coming. They are not the part of my writing. They are because of some difficulties in using the stylus on my notepad. So they're like AK, and it is equal to 0. Okay. So in this way, when you have calculated this, then you do this. You take again another derivative, and you are done with the first part. Then what about the next part? Okay, it is straightforward, because Lagrangian contains two parts. Remember, the free fields and the component or the term with the sources. Only the second part of the Lagrangian will contribute to this. Okay, because the first part does not depend on the field coordinates. The first part depends on this, first part of the Lagrangian, I mean, but not on this. The second part of the Lagrangian, which I wrote just before, depends only on the coordinates, right? But not on the generalized velocities. Okay, so in this way you can find out the second part, and the second part of this thing can be obtained. So I give you also as a problem to find it, which is easy, not difficult. Find this del L over AI. This is AI, remember, del I. Okay. So it is what del. Good. So del L by del AI. How much is this? L has something plus, or rather minus, because it will come with a minus sign, 1 upon C. And then I told you AIJI. But since I'm using I here in this, so I can change these notations to M and M there, because after all, these are just the dummy indices. So you can write it as what? You can write it as AMJM. Okay. And you put this thing, back in this expression. So put it back here and find out what is the answer. Right. Now, and also look carefully in the placing of the indices. This is a covariant, contravariant index, and here it is a covariant index. So it is better to take this index on the upper side. So when you take this on the upper side, you can also write it like M and JM, because you can take this index M on the upper side. At the same time, you can take this JM index on the lower side, because the two operations are done at the same time, so it does not alter the value of this. So here, when you do this, it becomes what? It becomes like AM, AM, JM. Okay, and this AI. Right? So what do? You can calculate its value, and let me show you at least by one example how do you do it. You write it what? You write it like JM. So you can take this JM outside if you like, and you can simply write del by del AI, del of AM, right? And this JM can be written here. And this value will be non-zero only if M is equal to I, and this statement is written as when M is equal to I. Okay. So when M is equal to I, you can have this value. Otherwise, you cannot have this value. So when M is equal to I, then you will have it 1. If M is not equal to I, you will have it 0. Right? So in the entire expression, the answer will be sustained only if M is equal to I. And when you put M is equal to I, this outside JM itself becomes JI. And this is the answer of our question, that this is equal to this. Okay. Of course, there is a factor of minus 1 by C also. So don't forget that. When you write L, in L you have another factor of minus 1 upon C. So here you will have minus 1 upon C, another term of minus. Write it like this, minus 1 upon C. Okay. So there is this term minus 1 by C into JI. This is this expression. So you will have calculated both the terms of the Euler Lagrangian equation, and finally you will get, as you can see, what you can see, it gives rise to a del I fik is equal to 4 pi by c and jk. Okay, now this is you all know the familiar inhomogeneous set of the Maxwell's equations. Okay, so there we are. We have got the Maxwell's equations on the basis of the Lagrangian. So we first chose the Lagrangian, and after making certain considerations for choice of the Lagrangian, we went ahead with the action principle and then into the Euler Lagrangian equations, and then we showed that the Euler Lagrangian equations are nothing but the inhomogeneous Maxwell equations. And then if you satisfy the inhomogeneous Maxwell equations, then the homogeneous Maxwell equations are automatically satisfied, right? And the homogeneous Maxwell equations are like this, is equal to 0, where f star ik is a dual, right? So you know that it is a dual field strength tensor, and we had always talked about the dual field strength tensor in writing the homogeneous equations, whereas these are the inhomogeneous equations. Okay, this is one thing. So you should at least try to do these, and also from here you can find out the conservation of charge, right? The local conservation of charge. Because if you take jk on both sides, like del k and here also del k, then you can show that this del k jk is equal to 0, right? So please try to show that del k jk is equal to 0, right? Now this is the local conservation of charge. So when I say charge, of course, the currents are also included in that. Okay. So please show this, and if you have any questions, I can discuss now. Otherwise, someone can add these questions to my previous list of questions.